Our last speaker of the day is Gianluca Paolini from Università di Torino, who will talk about profinite rigidity of crystallographic groups.
Thank you very much. It's a great honor to be a speaker, also because I am officially a logician, although I've been working in group theory for several years, so it's particularly nice, this invitation. This is joint work with Simone André, Davide Carolillo, which is my PhD student, and Rizos Klinos. And it's somehow a survey of 4 papers, which I will detail at the end. And so, as I'm a logician, I thought that it would be appropriate to explain how I arrived to this, also because we need some. But we need really a minimal amount of what's called model theory. Maybe most of you know, because there are many interactions within group theory, first order logic, but I will try to briefly recall such things. Also, I want to explain how I arrived to study the problems that I'm going to talk about, profinite rigidity, of course. So now this big slide just tells you what's a first order formula. Now it's actually easy to explain in words. You just have a term, another term, you say they are equal. This is an atomic formula. Then you just take negations, conjunction, disjunction, you put universal existential quantifiers, and you're done. All right, so this is what logicians consider in first order logic. We don't only study first order logic. And so then now I will do examples, but so now logicians like to write that this phi satisfies, G satisfies this formula phi with these parameters bar G in that way. We like it somehow. And this is the only thing we need to know. And also that a sentence is just a formula which doesn't have free variables. So all the variables are, of course, quantified away. We will at some point need also this definition, which is slightly more technical, which is the type of a tuple in a group, which is just all the formulas that are true of this specific tuple. We will need it later on. Now, very basic example, if you take a formula like that one, this defines the center, of course, no? Because you commute with everybody. So this is a formula in one variable, the solution set is the center. While this is truly a sentence, and it tells you that you are abelian. While this, for example, tells you that there are 2 non-trivial evolutions. While this is slightly more involved, but very easy, just tells you that there are at most 3 conjugacy classes of involution, for example. So this you can say. But it's highly non-trivial to understand what you can and cannot say. For example, is being hyperbolic a first order property, not by a sentence, but the whole theory. And there are very nice results. So this is just a baby version, but there are very many things that which you wouldn't expect are first order expressive. They actually are on certain classes of groups, of course. So the central definition for us logician is this of being elementary equivalent, which means that whenever you take a first order sentence in the language of group theory, of course, then this phi is true in A if and only if it's true in B. So this is an invariant, like the profinite completion invariant. We will see in a moment how this relates. Okay, so this is an equivalence relation refined for isomorphism, and oftentimes you want to understand which groups are elementary equivalent to a fixed group, for example, a free group. So, for example, let's take a very easy example. Let's take Z and Z2. Are they elementary equivalent? Well, if you think for a second about it, you can say this thing here with this formula. You can just say that G modulo 2 G is less or equal to 2, 3, 4, whatever. And in Z is of course 3 true this thing, but in Z2 won't be true. Actually, this has to do with finite quotients, and we will see that it's not by chance that we actually distinguish this group in this way by results that I will mention. Okay, so the free abelian groups we can very, very easily distinguish. On the other hand, you take a free group, well, First of all, you ask, okay, free cyclic group and a free non-abelian group, are they elementary equivalent? Well, very easily, one is abelian, the other is not, so you're done. And then you ask, all right, this is what Tarski did. What about you take two non-abelian free group, are they elementary equivalent? And this inspired a lot of work over the years, and this finally got solved in 2006 by Sela and independently Karlambovic and Myasnikov with a yes. And this is a very long sequence of papers because you gotta do a lot of things, you gotta prove some form of elimination of quantifiers and blah blah blah. All right, so this is one of the deepest results in model theory, I would say. I personally believe. But now you ask, what does this have to do with profinite rigidity? All right, if I didn't lose you yet. All right, I will get there if you are patient enough. And but to do that, I gotta mention Coxeter groups, and then you will say, why are you even considering this? But that's how I arrived to this. But thankfully, Olga yesterday talked about Coxeter groups, so I can just essentially skip this, although I will recall it quickly, also because the focus is on crystallographic groups. Anyhow, you have this. Olga yesterday rightfully used a graph, but you can also use a matrix. They are, of course, they encode the same information. It's just these are matrices which have one in the diagonal and are symmetric. And whenever you have such a matrix, then you can associate a group. So here I use the notation, a different notation, but it's like what Olga said yesterday. So it's the alternating word that starts with S in ST of length K. And now, so this matrix gives you a value for each pair. These are the generators, of course, these S's. And now how you associate to this matrix a group, Coxeter group? Well, you ask that each element is a generator, so the F of Olga yesterday is just with 2. And then you say that these alternating words that start with S and they start with T are of length MST, because the matrix tells you this information are the same. Okay? So this is how you define a Coxeter group. Of course, if, for example, you get this matrix, then it's just Z2 times Z2, Z2 to do with 2 elements. It's important then to denote WS a Coxeter system, so with the specified set of generators. Now, very quickly, you pass from these matrices to, for example, complete labeled graphs. So you just take the generators, and instead of looking at the matrix, you just put the number on the edge. This has the same information. So that's why if you saw Coxeter groups in places, then you see all these graphs. Now, to confuse you, there are two notations. This is the Bourbaki notation, which is the thinking diagram notation that Olga yesterday referred to, which forgets the label with 2 and doesn't write a 3. And then there is the notation which Olga used yesterday that doesn't write the infinity. Now, this is confusing. There is a reason, because, for example, the finite Coxeter group with this Bourbaki notation, they are much easily written. More easily. So we will follow this convention. Anyway, it's a convention, who cares? So the reason I did this is that I will talk about the affine Coxeter groups, and now I will show them to you. And last, if these graphs in this sense are connected, then the system is called irreducible. So it just means you cannot split it as a direct product. So also the finite ones, but here I want to focus on the affine. Irreducible Coxeter groups have been classified. This is very famous. This is related to thinking diagrams. We will see even more in later results about such things. But anyway, that's it. These are the only reducible abelian bifinite, also, as I'm going to say in the next slide, Coxeter groups. And this is very nice. So there are these infinite families, and then there are the sporadic ones. And it so happens, actually, that each one, that these are abelian bifinite, they are actually split, and each one comes with an associated finite Coxeter group, groups irreducible. And so they all have these forms, Zn, semi-direct product, W0, W0, and associated specific finite Coxer group, a crystallographic. Crystallographic. For example, the infinite diagonal group is Z, semi-direct product Z2 with the obvious automorphism, minus identity. So the irreducible affine Coxer groups are exactly the infinite abelian bifinite irreducible Coxer groups. There are also other ways of characterizing them. This is one. Okay. Now, and once again, what does this have to do with profinite rigidity? Really, now we are close. But first, I have to talk about first order rigidity, which is of independent distance, but we will see it's in this case very, very related. Now, this shouldn't be too crazy for this conference. It's similar to profinite. So we say that a finitely generated G is first order rigid. If you take any other finitely generated elementary equivalent to it, then it gotta be isomorphic. This is what's called being first order rigid. Now, asking this finite rigidity result just because of nonsense of logic is necessarily otherwise. Just use low and ice column. And unless the group is very easy to start. And now, by Sela's result and the other sets of authors, Fn is of course not first order rigid for n at least 2, because Fn plus 1 is elementary equivalent to it. But Zn is first order rigid. We will see in a moment why. And now finally, well, first I want to mention that this first order rigidity is very important, and there is a very famous result for us logicians, at least, of Professor Lubowski. Although this is not relevant, it's really something that we really appreciate as logicians. It's this very nice first order rigidity results on arithmetic lattices that is really renew the interest in this topic, and me myself, I started working on it after seeing such beautiful results. So really the reason why I arrived to talk about what I'm talking today is that I was studying first order rigidity for Coxer groups. And of course among the Coxer groups there are the affine Coxer groups, which I told you are very important. And so I naturally consider our affine Coxer groups first order rigid. By the way, I want to do a little bit of advertisement for this paper that I have with Simon André, in which we wrote many beautiful results on first order rigidity for Coxer groups, which are outside of the affine world, but this won't be relevant. But if you are interested, you can ask. And now, what's the point? So it so happens that Auger in '88, I think, proved that if you have two finitely generated abelian bifinite groups, then they are elementary equivalent if and only if they are isomorphic. They are profinitely isomorphic, if the profinite combinations are isomorphic. And since finitely generated abelian bifinite groups are residually finite, then we see that this is the same thing. Study this problem, which is the problem I was studying, motivated by logic, naturally. It's the same thing as asking about profinite rigidity. All right, for abelian bifinite groups. And this works almost only for abelian bifinite groups, in the sense if you are polycyclic bifinite group, actually G and G hat have different existential theory. But if you are abelian bifinite, actually G is what's called an elementary substructure of G hat. So I'm just saying that this nice thing is essentially works only for abelian bifinite, or at least among the polycyclic bifinite groups. But there it works. And affine Coxer groups are, well, they are even split, no? So actually that's how we arrived to the solution, which was independently solved by Corson, Hughes, Moller, and Marchese of the problem posed. So with Rizos-Klinos, we solved this problem, proving that they are first order rigid. So our proof, yes, uses model. So we got two independent solutions to this problem. One was coming from logic, which we thought and still think is particularly nice. Now, really, the proof, to be honest, uses, of course, model theory, but it uses integral representation theory, and it uses crystallography. So really, after I did this proof over the, I don't know, 1 year, 1.5 years, 2 years, I thought about, well, what's behind really this proof. So recently I posted a new paper on arXiv, and mostly I will talk about this. But actually, so this ends the introduction. So I will talk about the profinite rigidity in the sense of pushing this result as much as the methods allow. And then talking about profinite homogeneity, and you might wonder what's this? Well, it's something we introduced, motivated by abelian bifinite groups. And then, well, just one slide on the genus problem for finitely presented modules. It's very nice that yesterday there was a talk related to this, so I'm very happy about it. And we should join forces because, yeah, but this only if we have time. But it's, for me, the natural development of this idea. Now, what's a crystallographic group? Well, we will soon give an abstract characterization, but just, I guess, one of the official definitions is that an affine, first of all, crystallographic group is a subgroup of the isomety group of a finite dimensional real Euclidean vector space, which is discrete and co-compact. Actually, Zassenhaus proved that an abstract group is an affine crystallographic group of dimension n, if and only if it contains a free abelian subgroup T of rank n that is normal of finite indents and maximal abelian. So really this group sits in this short exact sequence. So this is called the translation subgroup. This is the group we are after. And this is the quotient, the point group is called, which is a finite group. So that's it. These are what's crystallographic. And this is Z. These are crystallographic groups. You might think they are easy. They seem easy, but they aren't that easy. So it's important, this notation, because it's crucial, the distinction between what we call the translation subgroup and the translation lattice. Now this is a notation. What's important is, and this is very, very related to what was said yesterday with the short exact sequences here, it's really an example of that, of course. Now we have that the point group, of course, acts by conjugation on the translation subgroup, and so this is an integral then representation, actually, of this group PW, which sometimes we also call W0, just because we have constant groups in mind. So what's important to remember is that then when you have a crystallographic group, you do have an integral representation, or equivalently, of course, a finitely presented ZW0 lattice. And here I mean, of course, as a module. So you have this module. And this, so remember, when I say lattice, I mean the module. This is important. And actually classifying crystallographic groups is the same, up to abstract isomorphism is the same thing as classifying them by conjugation of some affine motion. Okay, so you can choose either to represent them as affine groups, or you can just study them abstractly. They are the same thing. This is related to important problems. There was an important problem on how many crystallographic groups there are. All this Bierbach, this is true because the Zassenhaus result is Bierbach 1, and this is very classical, all this. But now we come to the connection with profinite rigidity. Then we say that true, then lattice, well, yeah, LL prime ZW0 lattices, that they are in the same genus if they have the same finite quotients as modules. So it's really as was mentioned yesterday. Now, a crucial lemma that also we proved in this most recent paper also was proved by others, I guess, but still the point is how we use it, really, is that if you have two crystallographic groups, W and W prime, you can read that they have the same profinite completion. Then they have the same translation subgroup, they have the same point group, but really what's important is that after some obvious identification, the translational lattices as modules are in the same genus. All right. In your sense. So this is the real deal, is this. Why is this the real deal? Well, because this is essentially number theory now, because integral representation are a topic of study, integral representation theory. And there are very important examples where profinite rigidity fails. So this is, for example, very famous. There are many more results, but I mentioned this because it's easy to state. Even a cyclic group of order P can act on ZP minus 1 with P at least 23, so that actually you are not first order rigid, or first order not profinitely rigid. So it's non-trivial, not all split crystallographic groups are profinitely rigid. So what's more interesting possibly is actually that, and this I mentioned this also yesterday, there are crystallographic groups which have isomorphic translation lattices, so they are isomorphic as modules, but the extension, which won't be split, of course, are in the same genus, and the groups are non-isomorphic. So the smallest example I know of is with the point group of order 55, so it's not a big, and it's the Frobenius group of order 55. So we see that although they seem easy, these groups, the problem of profinite rigidity is not easy at all. First of all, we have the genus problem, and I will say something about this, which is hard. And then also there are non-split extensions that complicate the situation even more, because of this that I just said. So it looks easy, but it's not that easy. And really on the genus problem, really there is a chapter in this classical book, and there are many results, many characterizations. When you cannot do, this is really now, it was at the time a classical topic. Now I'm not so sure anymore, but it's a deep part of mathematics. Now, anyhow, we want to understand how much we can push of this result, because we arrived to this, it seems natural to do that. And now, if you look at a fine Coxeter group from the point of view of crystallographic groups, actually they are very, very special. Well, irreducible affine Coxeter groups. Because anyway, by some results, you can just reduce to the irreducible components for any crystallographic group. Now, first of all, they are split, the affine Coxeter groups, and also, and these 2 points are the ones that I'm going to be focusing about, the associated integral representation are actually absolutely irreducible. Actually, that's really the point of them being profinitely rigid. And also they arise from root systems in the sense of Lie theory. And now we want to understand in particular if the proof that I had found was actually had something deeper, more crystallographic in it, let's say. But it had nothing to do with Coxeter groups after all. Well, more maybe with as we will see, crystallographic groups arising from root systems, yes. Now, all right. So I have to quickly explain what's this, although maybe you already know these things. When you have a ZW0 lattice, we say that it is irreducible if it's really simple as a module, so it doesn't have proper submodules. And we say that it's absolutely irreducible if you tensor with any extension of Q, K, then you are still reducible. So when I write this QL or KL, really I mean this tensor product, or if you like more representation theory, of course an integral representation also lives as a rational representation. And so, well, you see, now we can just say that a crystallographic group is absolutely reducible if the canonical associated lattice, in the sense of modules, is absolutely reducible. This is what we define that to be. It doesn't have to be smooth. We just look at the module and we ask if it's absolutely reducible. Now, actually, working on the proof, I realized that the core of the proof is actually that if you have a finite direct product of absolutely reducible split crystallographic groups, they are profinitely rigid. And so that's why the affine Coxeter groups are. So from this perspective, it's much more maybe. It makes more sense to me in my mind. But this is not the end of the story, actually. We wanted to do more. My PhD student. I wanted to understand more. So, what about non-split extension? And what about other integral representations that arise from root systems, actually? These aren't the only integral representations that arise. So this is what we want to understand. By the way, crystallographic groups of dimension less or equal than 4 are all known to be profinitely rigid. But more general results of this kind, I don't know. The smallest split is of that order 22, dimension 22, because it's 23 minus 1. And the one with the, the one with the isomorphic translation lattice, now I don't remember the dimension. But, so really, there are examples. So I gotta explain what it means to arise from a root system. Although I won't define root system for reasons of time. Now, but we just did this simple definition. What's essential and what's a reflection, I guess, you know. So, a subgroup of the orthogonal group is essential if really the points that every element of W0, the points that are fixed by every element of W0 is just a trivial vector, okay? And a reflection, well, is just a linear one automorphism such that pair of 1 minus s has dimension L minus 1, so it means that it splits the space in L minus 1 and 1. And then it's an involution. So this is what we need. Because now we say that W, the crystallographic group, arises from a root system if, of course, it admits a realization such that the point group is essential and generated by reflections. So now it's unambiguous what's going on. Now, of course, by classical, extremely important works, these are actually, this W0 is the real group of some root system, which I won't define what's a root system, but it's a classical notion from the theory. And then we say that then W arises from an irreducible root system if the root system is irreducible, which is a technical condition, but it makes life easier. Okay? So this, we look at the affine realization and we ask this student that the point group is really a specific realization. Of course, the affine Coxeter groups are of this kind. This is how they arise. And now, actually, in these very nice papers, one from '73 and one much later, the crystallography of Coxeter groups was developed. So they really classified the crystallographic groups arising from a irreducible root system. So first Maxwell did it, and then Martinet computed explicitly certain representatives that Maxwell had. I will show you two tables that counted the certain numbers of isomorphism classes, and then Martinet gave representatives. So these are classified. Of course, all the affine Coxeter groups live here, all right? And this classification is very nice, rather technical, and now don't get scared, but I will show you two tables. Of course, you don't need to understand them now, but really, you see, these, for example, first you classify the lattice, it means the modules, if you like. So these are the types of the root systems, no? This AL, BL, CL, DL, blah, blah, blah. And here it tells you how many there are of inequivalent lattices. Okay. So as modules. And then for any such, so this is an integral representation. It means all the integral representation in my terminology. So these are all the integral representation that arise, and not only the integral representation that arise for the affine Coxeter. This is a more general context. And then actually, but here I show only some, there are for each one many extensions, some split, some non-split, and really those are explicit representatives. Of course, we don't have to understand them, but as affine realizations, really, those are the representatives that are shown explicitly. And so really we know what, well, to some extent, what are these groups. And now what the second main rigidity result that we prove is that actually finite direct rods of crystallographic groups arising from an irreducible rod system are profinitely rigid. So all these groups. So you take all the integral representation, all the split extensions, of course, but also the non-split extensions. Any two you can separate. So this is really, I think, the other reason for the proof that I had found of the affine Coxeter groups. Maybe this is the deeper reason why the affine Coxeter groups are profinitely rigid. So, and really, for each pair of groups, we do find a sentence that separates them, and we literally do that. So our proof uses model theory. Of course, I'm not claiming that it's necessary to use it. It's just a proof that we found. So we thought that this was nice. And this is the end of the first part of the talk. Now we move to something which is more model theoretically inspired, but I thought maybe it could interest some profinite. So, and this one has to enter a little bit in the perverse mind of a logician to understand this definition, although I think it makes a lot of sense. So, really a property that in model theory of groups has received a lot of attention in recent years is this one, of being homogeneous. There are many notions of homogeneity in model theory, but now let's just consider this. We say that a group A finitely generated, say, is homogeneous if, whenever you take any natural number, you take two tuples of length n, whenever they have the same type, this means that they satisfy the same formulas, you remember from the second slide. This happens if and only if there is an automorphism that sends this tuple to the other. Of course, the right implies the left, but the left doesn't imply the right in general. So this means that really, in passing to elementary extension, you don't alter the orbits. We will see another equivalent definition of this that is maybe more group theoretical, and it will inspire a definition. But this is the definition. Now, this really, to us logicians, are important. It's an important notion. For example, this paper in Duke showed very nice of Perrin and Sclino solving a problem of Sela, showed that free groups are actually homogeneous in this sense. There is literally zero strongly homogeneous, but it's just what I call homogeneous now, because they make a small distinction, which doesn't matter here. So really we care. This is something very important for us. Now, also here, how does it connect to profinite rigidity? You will see in a second that for abelian profinite groups it does. But first of all, I want to mention this equivalent definition of being homogeneous. Now, actually, when we do model theory, we have our model M, which would be the finitely generated group we are studying, but then we have what's called the elementary extension, big elementary extension, saturated elementary extension. So an elementary extension that relies a lot of types. And actually then, from the perspective of this, what's called monster model, so a sufficiently saturated model, actually a group is homogeneous if whenever there is an automorphism from the monster model that sends, say, a tuple U to a tuple V, then there is already an automorphism that sends U to V. It is non-trivial that this happens. Because anyway, the types, what I call types, are just the orbit of this large saturated model. So really, if you look at this perspective, I think it's even more natural. What's a type? But you see, they don't need to match these orbits. And in fact, this is by the definition, which is not a vacuous definition, because I will mention why I use it, that well, a priori makes sense just for any finitely generated residually finite group. We see that G is profinitely homogeneous if really what happens there happens. It means that if whenever you take two tuples, if there is an automorphism of the profinite completion that sends one to another, then there is already an automorphism of U that sends U to V. So there is a matching. It doesn't alter the profinite completion, the orbits. We will see that this is non-trivial in the abelian bifinite case. And so, but this is really, as a definition, is just for any finite generated residually finite group. Now it so happens, this is another result that we proved with Simon André, that a finitely generated abelian bifinite group is homogeneous in the sense of logic if and only if it's profinitely homogeneous. So this is also nice. As elementary equivalence was profinite rigidity, well, or first of rigidity, profinite rigidity, also this logic homogeneity correspond to this profinite homogeneity. And then, actually, in our paper, we studied larger classes of groups. We proved that affine Coxeter groups, hyperbolic as chromo even Coxeter group and hyperbolic one-ended Coxeter group are all homogeneous in this sense of logic. But if you like, as a corollary, you deduce that affine Coxeter groups are profinitely homogeneous in this sense. And then you say, okay, but they are all are maybe, whatever. What's the point of this notion? But that's not the case. This is very subtle. Because if you take G and G prime, which are non-isomorphic split crystallographic group which are profinitely isomorphic, then actually the direct product of them is not homogeneous. So when you pass, this is related to the twist that was mentioned yesterday somehow. But when you pass to the profinite completion, you can find automorphisms that alter tuples. Although interestingly, in the example we have, they come from the torsion of the group. But it does happen. So they are, if you like, they are not profinitely homogeneous. If you take G1 times C2 in the same genus. And now the question really that we leave open, we did not solve it in full, is are, for example, profinitely rigid crystallographic groups homogeneous? Of course, this is not profinitely rigid. And also, actually, even it's open if it's irreducible, is it profinitely homogeneous? But we do have strong results, though, partial results. For example, if it's split and irreducible, then the homogeneity has to come from the torsion, actually. So not from the translation sample. But still, the problem to us, it doesn't appear very easy, but maybe you have other techniques. In fact, we don't even know a proof of that the affine Coxeter groups are profinitely rigid, which does not use logic, because really we prove that they are homogeneous in the sense of logic. Once again, maybe there is another way. But really now I'm scared of asking this question to such a audience, but still I hope maybe you will solve it in 5 minutes, but then better than I know. But really, for example, I have no idea are finitely generated free groups profinitely homogeneous in this sense. Huh? All right. So if two tuples are, there is another morphism of the profinite completion that moves the tuples. That is there one from the free group itself? I have no idea. I have no idea. For the abelian bifinite group, I characterize when this happens. I have example when that doesn't happen, so I feel rather comfortable here. I don't know, but I see the point of at least settling this question, although I don't know how to do it myself. All right, so we are almost done, maybe done. Yes, we are done, so we will have a longer break. But now, for me, the future work that I see from my perspective on this, I think you realize that the techniques are really module theoretic. This doesn't come as a surprise. And the point is really to now develop really at face value a general theory of when two finitely presented modules are elementary equivalent or profinitely isomorphic. Well, this should be an isomorphism. But anyway, the point is that, as it happens for crystallographic groups, for many modules, actually being elementary equivalent and this with an isomorphism are the same thing. This happens when the pure injective envelope is the profinite completion. When this happens, there is this match between being elementary equivalent and being profinitely rigid. And really, with Ivo Herzog, which is a famous model theorist, module theorist, oldest non-retired module theorist, we really started developing this general theory of when two finitely presented modules are even profinitely rigid. And this has a lot to do with endomorphisms, and of course, one of the things we want to do is to generalize what is done for the genus problem, that you characterize profinite rigidity in a certain technical way with class groups and things like that. And it's nice to discover that this already started, and of course, we will try to join forces or take inspiration from each other. But I think that maybe these, well, even from the talk of yesterday, I realized that such a theory, such results could actually be used to find unexpected, at least to me, new profinite rigidity results for groups. No? Because maybe in certain cases, you reduce to consideration of modules, and having such a theory, well developed, inspired by logic, but really truly you can just look at this with isomorphism, that there is a title, could be of help. So that's what I intend to do with that. And this is it. Okay, so I finished too early, but that's okay, I guess. And these are the papers.
Any questions?
So you said that for virtually abelian, finitely generated virtually abelian groups, first order rigidity and profinite rigidity are equivalent, and
Yes.
you said that it's almost the maximal class of groups where you said that it's almost like the largest class of groups where this is true. But my question is, do you have like a one arrow of implications for maybe a larger class of groups?
No, well, this I hope will answer the question. Polycyclic bifinite. Then G is an elementary, well, actually, G is existentially equivalent to G hat if and only if G is abelian bifinite. for polycyclic bifinite, otherwise there is an existential sentence. And this breaks the whole thing for polycyclic bifinite groups. And by the way, by a famous result of Lubowski, G hat is elementary equivalent to H hat for G and H finitely generated if and only if they are isomorphic. And so really in the polycyclic bifinite world, this breaks this nice connection. So I think really you cannot use it as far as I know.
But is there a class maybe where you could say, okay, if you know that it's profinitely rigid, then it's definitely first order rigid, like only that implication, for instance.
But really, if they have different theories, it won't tell you anything, I think. But, I see what you're trying to think, but really, I don't see. Of course, but today we were discussing with this man that I don't know, myself, if F, but I'm sure this is no, but I don't know if Fn is elementary, existentially equivalent to Fn F, but I'm sure it's no, but I don't know. Because this is only for polycyclic bifinite groups. Or for any limit group. Actually, I don't know this. If you know, let me know. So let's put it this way: for polycyclic bifinite group, only for a binary bifinite, you can use directly these methods. Of course, passing to modules is very different because modules work fine, but you just have the module, so you gotta do these tricks, the group theoretic part that you did, which is non-trivial. But still, in fact, I think I will focus on doing the things because for modules it's nice. It's just whenever the pure injective envelope is the same thing as the profinite completion, really that's the same thing. And these modules might arise for even as you do larger classes of groups. So I would rather maybe go in that direction. Although it's interesting just per se, I mean even this. But yeah, it would be nice if there were a more for a larger class of group connection.
Just a comment that I believe that Alex and Mary and Niravni proved that non-uniform arithmetic higher rank lattices first order rigidity. If they're first order equivalent, then they're profinite.
If they are first order equivalent, then they are. Yeah, I know this other paper, but I haven't looked. No, this I have to look at this. I see. So if they, let's see if we agree on that.
You use that the congruent subgroups are definable in first order logic as product of powers to deduce that if two lattices have the same first order theory, then they have the same profinite conclusions.
But on the other hand, they prove that they are rigid. No, well, maybe other ones because.
No, it's an open. I think it's an open question whether they're rigid.
Well, I guess you know my work better than I mean, what that if they are the same elementary theory, then the profinite completion is isomorphic. Oh yeah.
Certainly for SLM.
Yes. This is true. This was really the starting point.
So you mean for all arithmetic classes? Can you repeat the statement?
I believe it can be general. I believe the first result was for SLNZ, but then it was generalized to this class, non-uniform higher rank. The proof, I believe, generalizes.
Right, but among these ones, there is only one because they are first order rigid. Among these specific ones, if they are elementary equivalent, then they are isomorphic, so there is one. But for other things, being first order rigid means this, so even if they are one. But or maybe I misunderstood the remark. But yes.
I just have a comment.
Yeah.
The term of homogeneous profinite group already exists. So
Oh, so thank you for telling me this. What is?
one has to be careful in this
All right.
term.
We will change it. Well, okay. What is meant? Sorry, I didn't.
There it means that if you have a group and you have you go to the function of all simple groups that appear as a quotient, and then the number of these simple groups should be the same for every simple group. That's what means homogeneous.
So it's very different.
No, it's absolutely different.
Okay,
right?
or we
That's
will
why
say
the-
maybe we will say
perhaps one
orbit homogeneous. Maybe we will say. Or
well,
something.
whatever, I don't know. But
Yeah,
I mean,
yeah. No.
you can look there.
I will look
there,
at the,
and
I
maybe-
didn't.
maybe
Okay, I will
they
look.
change because it is applied to absolutely different
Yes, yes,
situations.
yes. No, yes. Thank you. Absolutely, thank you.
Any other questions? Then let's thank the speaker again.